In this video, I want to talk about using equations to represent functions. Equations can help us build functions succinctly, and they're very helpful whenever our inputs and our outputs are both numbers. Traditionally, we let x represent the inputs and y represent the outputs. However, we can use other letters as well. The independent variable is the variable used for the inputs. This ranges freely over all allowable inputs, so we get to pick what this is depending on what allowable inputs we can use for our function. The dependent variable is then the variable used for the outputs. And this is known as dependent because it depends on the value of the input in the independent variable. So we decide what we're going to put in for our input, the independent variable, and then our output depends on our choice of input. A lot of times there is a natural choice for which one is independent and which one is dependent. For instance, if I am looking at a function that looks at the distance traveled and the time we have been traveling is independent, and the distance traveled depends on how long we've been traveling. We can't just pick how long we travel and then time depends on how far we have gone. Instead, time is our independent variable and distance traveled depends on how long we have been traveling. On the other hand, sometimes you can choose which is which. For instance, if I want to look at a function that compares a wife's height to her husband's height, it does not matter which one is independent and which one is dependent, since one of those is not going to depend on the other. In order to actually write the equation, we're going to start by picking an independent variable, and typically this is x. We then write an expression in x for the output, so we determine how we get the output from this x, and we write some expression. We then need to pick a dependent variable, and usually this is represented by y. Finally, we can write the equation as y is equal to the expression in x that we got from our second step. As an example, if we want our doubling function, we have our input x. We are going to double it, so multiply it by 2, and that gives us our output. Our equation would be y equal to 2x. On the other hand, if I have my independent variable x, and this time I want to just increase it by 1, I could have the equation y equal to x plus 1. Functions can take other forms as well. For instance, I can have something like x times y equal to 24. This is not in the form y equal to an expression in x. However, it does tell us how x and y are related. And in fact, we can rewrite this. Is y equal to 24 divided by x? So functions may not always be written as y equal to an expression in x, but they can be written that way. Let's consider a function like y equal to x squared minus x minus 2. We can make both a table and a graph from this equation. The idea is we pick some inputs, some values for x, and we determine the corresponding output for y. I'm going to let x be -3, -2, -1, 0, 1, 2, 3, and 4. And then we're going to plug these into my equation. So for instance, for -3, I would have -3 squared minus -3 minus 2. This is -3 squared is 9, plus 3 minus 2 is 10. So this output would be 10. For -2, I would have -2 squared minus -2 minus 2. -2 squared is 4, plus 2 minus 2, which is 4. So the output for -2 would be 4. For -1, I have -1 squared minus -1 minus 2. -1 squared is 1, plus 1 minus 2 is 0, so the output here would be 0. If we input 0, I have 0 squared minus 0 minus 2 gives me negative 2 to be my output. If we input 1, I have 1 squared minus 1 minus 2, or 1 minus 1 minus 2, which is negative 2. And you can go ahead and plug in 2, 3, and 4, and you will get 0, 4, and 10. Now that I have this table, I can graph the function. My first point will be negative 3, 10. I then have negative 2, 4, negative 1, 0, 0, negative 2, 1, negative 2, 2, 0, 3, 4, and 4, 10. And from there, we just try our best to connect the dots. Didn't do a great job here, in a smooth line. And we have the graph. The graph is a visual display of all the solutions to a function's equations. So my inputs and outputs are given as points as x, y. And these are things that make the function true. So if it is a corresponding input and output, if it's at a point on this graph, then it satisfies this equation. In addition, everything that satisfies this equation is going to correspond to an ordered pair on this graph. So a graph is just a visual representation of the solutions.